Yes. So we may have a better flow based on what we started looking at. So after looking at grading, I'm now going to move on to unit protection. In terms of the tables that you had last week, were you able to confirm those values that are there? Went through the calculations? Yes, no, maybe so.
No, I haven't as yet.
Well, yes, sir, but what sir, I kind of like worked out one until I found the answer. Then I use that same approach for the rest of them without actually fully understanding what I did.
Okay.
Sir, I wish that we had the recordings to actually go back to it because I noticed that you haven't posted last week's recordings.
That one is a little strange because it is up and I saw that it got 24 hits. I'm not too sure what happened. Anyway, we'll remove it and upload it again. But it's important. I'm surprised you have allowed a week to pass without looking at it. You don't want to fall behind with this module, all right? It might not look like it, but you have gone through quite a bit already, huh? Yeah, so I would prefer if you not allow it to pile up. All right, so we looked at grading over current relays. What you would have done in power systems, so we took it a step further. So what happened to the other cameras? So Johnson is great. Anyway, we took it a little further and looked at the grading exercise. And of course, some of what we went through in the grading exercise, you would have been, well, not in that sort of detail, but you would have been looking at some of it in lab number 2, yeah? So today we're gonna take it one step further by looking at unit protection. We have mentioned this in a general way, but we're now gonna come back and look on, in particular, high impedance differential schemes. But just to give a general background as to what we're gonna be looking at. If you had gone through the grading exercise, what you would have noticed is that as you went back towards the source, closer you got to the source, and you went upstream, the time dial settings became larger. And of course, the operating times going back to the source also became larger. What that is telling us is that for you to use grading or the use of grading throughout the system will at some point not be as beneficial or be ideal in terms of operation as we would like. Good? Because if you're always having to give consideration to the downstream relay, meaning allowing the downstream relay to operate, then you're going to have a multiplier effect coming back to the source. And ultimately, you lose that effectiveness. So the graded systems, simple in principle, but it will not provide the sort of overall protection that we are seeking. And that stems from two primary reasons, as we have put here. For complex networks, look, what we looked at last week was just a radial feeder, right? So just a feeder going into a community. That's quite simple. And you recognize how involved the whole activity was. So when you now start to think about interconnections, right? and for you to set your relays so they are giving consideration to other relays within the system, you end up over time, after a while, being almost counterproductive. And well, this is just summarizing what we're saying, in that with your grading systems, you may end up having trip times, as in the case of possibly relay A from our diagram, which is much too long, and therefore may result in problems on the system. So we have to find a method, or we have to find a way to quickly remove portions of the network and therefore limit damage or limit outage, right? Because that is our primary objective in terms of the protection system. So when we now talk about unit protection schemes, that unit protection is limited to one part of the network, yes? And once there's an internal fault in that protected portion, then it's going to trip. So there is no need for coordinating the protection system with the protection system of other parts of the network. Once the fault occurs on the item that is being protected, the component that is being protected, then you will have trip. But at the same time, and I think we have said it before, maybe not formally, at the same time, you want to ensure that faults which are external to the equipment or the portion of the network that they are protecting, faults external to that, you want them to remain in operation. Yes? And remain in operation if you have faults that are external. And we kept referring to that as through fault currents. So if you have a transformer, to the extent that the transformer can handle the fault current, now speaking about physically being able to handle that level of current, yes? You want the transformer to remain in service because it will not necessarily be supplying only one line. So the transformer may be the source for 3 feeders. The fault may be on 1 feeder. What you want to happen is that the protection on the faulted feeder should operate and the other 2 remain in operation. Fair enough? Now, if you were to remove the transformer, it means that you would have taken out all 3 feeders. So you want to be able to allow through fault current. All right, so faults that are external to this protected component or protected section of the network, currents must be able to pass through them without them tripping. And as I said before, the biggest benefit from unit protection is that there is no need for coordination. There is no need for handshake with any other protection system within the network. Okay? So in terms of the foundation, 1, coming from what we saw last week with the graded systems, it becomes a challenge dealing with complex networks. 2, we're also saying that because of the grading, in terms of the operating times of some of your relays, they may end up operating after too long a time and therefore not remove faults quickly enough. For the unit protection, it is quick. There's no need for coordination. But one of the key requirements is that they must be able to allow operation to continue if the fault is external. Bearing in mind also, though, that I mentioned the transformer. Whilst you want to allow through fault currents, and I did make the point that the transformer must be able to physically manage this through fault current, you would militate against that by using overcurrent relays. So you do have overcurrent relays on the transformer. Yes, Mr. Buchanan.
Sorry, not to cut you. Just a quick question. When in terms of complex networks, that would refer to like networks with like multiple branches, or that's in terms of
Yes,
the type of treatment? All right. Thank you, sir.
branches. All right. So going back to the transformer, what we're saying is that yes, you will have the unit protection. Yeah, it will allow fault currents to pass through. However, there is a limit because the windings themselves, the size of the windings, there's a limit to the amount of current that can safely pass through. If it exceeds a certain value, then it may cause a breakdown of the insulation that you're using. Again, depending on the wavefront that you're dealing with, right? You have insulation damage and you end up damaging the transformer. High currents through the transformer can also result in physical damage to the unit. And we'll talk about that when we delve a little more into transformer protection. All right. Okay, so those are some of the key considerations for your unit protection. And what we have here is a basic outline of what unit protected, a protected unit or unit protection looks like. So here we have the protected unit. We have one CT, we have two CTs on either side, and then we have your relay. So that represents your relay. All right, so it's basic setup of your unit protection. And the key principles here are that one, if the current flowing into the protected unit is the same as the current leaving, then the fault is not on the protected unit and the protection should not trip. And then two, if there's a difference in magnitude or phase between the input and output, then the fault is in the unit and the protection should trip. All right? So again, I'm trying to remember, I think, yeah, you're the group I was talking to about the magnetizing curve. I think so. All right. But there's a property, we talk about retentivity, which is an important property for your transformers. So when you de-energize a transformer, the transformer will maintain some magnetism in its core. So in terms of the core of your transformer, what you want is that it should be easily magnetized and should not readily lose its magnetism. All right? So the reason I mentioned that is because when you de-energize a transformer, if the level of magnetism should fall significantly, then in re-energizing the transformer, what you will have is that you have a significant current at the input. But of course, we know the principle on which a transformer operates. Yeah, mutual inductance. So you'll have significant current going into the input, but you won't have a corresponding current at the output. Yes, we'll look at it in more details later on. What that represents is what we refer to as inrush. So you'll have this large current at the input, very little at the output, but the transformer is operating with, has unit protection. But based on what we are saying here, if there's a difference between the input and the output, then you should trip. But obviously what I just described would be a normal operating condition for your transformer. and you certainly would not want it to trip. So in that, or in those cases, we'll have to find other ways apart from just looking at magnitude, current in, current out, to determine whether or not we should trip. With me? I will delve into that a bit more later on. So the condition is, if the current going in is not equal to the current going out, then you'll have that current difference, meaning that the fault is on the or in the unit being protected, or in the portion of the network being protected, and you should operate. Okay, that's a basic principle. But of course, there's nothing so simple in power systems. All right. Some of the components are items within your power system that we use differential protection on. Yep. Would be your generators, your bus bars, your transformers, your feeders. Now the feeders may look a little impractical, but we'll talk about that in a few. All right. So you have your generator, your bus bar, your transformer. These are the ones that we readily see the differential protection system being used on. And the two types of differential systems would be a circulating current and the balance voltage. In some texts, you might see it as voltage balance. Right? So you have your balance voltage schemes or your voltage balance schemes, and you have your circulating current. Our main focus this afternoon, this evening, would be on your circulating current. All right. All right. Now, this is just going back to what we showed earlier. So you have your CTs on either side. Yep. CT1, CT2. And of course, IS1 and IS2 would represent the secondary currents from these CTs, which would come to your relay, the difference of which would result in operation. Your pilot wires are just the connecting wires between the CTs and the relay. And so, well, I actually made some, I made contact with the utility companies. In the absence of us physically going there, I'm seeking to get them to do a little video presentation where we'll walk through the substation and taking some shots, and so you can get an appreciation for it. And the reason I'm mentioning it, because if you were to go in the substation, you would actually see the area through which these cables will be coming from the various devices on the plant, on the substation, into the relay house. All right, and that's where all the wires will be coming from the CTs back into the relays, which are in the relay house. Okay, and that's what all of this is about. All right. So for a healthy circuit, meaning there's nothing happening within your system, then I1 equal I2, assuming that the CTs are identical. Of course, this is true if the current on either side should be the same. In terms of the bus bar and your generator, the currents on either side should be the same. But in terms of your transformer, that's not the case. The currents will be based on the turns ratio of the transformer. All right. So if you have identical CTs, then the IS1 would be equal to IS2, which implies that your relay current is 0. So under these conditions, meaning no fault on your system, then that's what we would expect. However, if we do have a fault, then obviously IS1 will not be equal to IS2 because you have a fault on the protected unit. And I say on, but in, you know, on, in, you know what I'm saying, yeah? Finish with this? Yeah.
Yes, sir.
So if we have a fault, and let us assume that the turns ratio, they're ideal. And note, I'm very careful in repeating. You know, we talk about ideal, yes, because we know that that CTs are electromagnetic devices, and so there are going to be some errors. And we know that. We haven't spoken about errors already. But in terms of introduction, we assume here that they are ideal. You know, what they present as an output is based on ideal conditions in terms of their turns ratio. So with this said, because the fault is on the unit, the protected unit, then you're going to have current flowing into the fault. And so in this case, the relay current would be 10 amperes. All right? All right. Now, that represents the operation for your circulating current scheme. But of course, we mentioned that there are two schemes. So you have your circulating current and you have your voltage balance scheme. All right. And that's your voltage balance scheme. Now, as shown, there's some details that I have left out. All right, but we'll come back to it later on. And so let's take that from it, please. Take this from it, please. All right, now for the voltage balance scheme, basically what you have are two CTs connected in series of position. All right, and if voltage VS1 and VS2 are equal, then there is no voltage drop or difference in potential. And so there will be no current flow through the relays. All right. And again, in a few minutes, we'll just expand this diagram a bit to show you some additional details in terms of the operation and when we would end up using the voltage balance scheme. All right. So in terms of note, if you wish to write that, or if you had taken a note based on what I said earlier, for your VBS, VS1 is equal to VS2, and well, for a healthy circuit, and therefore you have no current flow through the relays. But we want to go back a bit to the circulating current scheme. Suppose I could have made it a little easier for you today and give you these diagrams beforehand. But yeah, we won't be long today. We won't be long today. We're almost halfway through already anyway. Yeah. So this is an expanded view of your circulating current scheme. All right. And let's just pull some things together. Although I have redrawn it, although I've redrawn the CT at either end. All right? What this represents, what all of this represents, is the secondary side of your CT. So this would represent the excitation winding. Yep. And we are just showing the X since X is much larger than R for that, for the winding of your CT. S here would be the secondary. Yep. And if you remember how the CT you had, right? And then that was R's. And then we went to your relay down here. So if you look at this, you really realize it's the same thing, yeah? Right? So yeah, I finally figured out to operate this thing. Boy, tell you. Anyway, we have the excitation winding, we have the secondary, and then RWG is the wiring, yes, between the CT and the relay. Because as we said, you do have physical copper wires going from the equipment into the relay room at the substation. All right. And our focus for the circulating scheme is to determine RR. All right. So what are we concerned about here? We spoke about having ideal CTs, yes? And if we had ideal CTs, then what we will end up having is a potential at the relay, yes, of 0. And by identical, it means that the secondary resistances would have been equal. All right? So if we had identical, ideal, and identical CTs, then the potential at the relay point would be 0, and so the relay would not operate. All right? However, from a practical standpoint, we will not have identical CTs. Yeah? And so what you would have is that the as a result of the difference in the CTs, yeah, you will then have spill voltage. So our relay, which remains, for use of a better word, it remains at the center, would now have a residual voltage across it. And this would occur without a fault being present. So it means, therefore, that there has to be not just the presence of a resultant current through the relay. All right, we have to move beyond that. We can't just say, well, once the current is non-zero, that you will have trip, because you will have a current flowing by virtue of the fact that the CTs on either side are not identical. Are you with me? Because we're dealing with an electromagnetic device. Yeah. So just by virtue of the CTs, you're going to end up with having a threshold current for your relay. So there is a operating current for your relay. So it's not that it operates once it is non-zero. There will be a minimum current. that will cause it to operate. Right? But still, spill current occurs just by virtue of the equipment we are using. However, what is of greater concern is what happens when you're dealing with transients. What happens when, because we're talking about a system that has significant inductance. So we have inductance, we have resistance, right? And depending on what we are protecting, we may end up with some capacitance. So the potential for transients or transient flux is increased. Yeah. Now, the consideration is not so much about even the capacitance, it's really about the inductance and the resistance. And we looked at this earlier when we were looking at the transient response of your CTs. Okay? And we said that that was dependent on the ratio of the inductance to the resistance, or the X to R ratio. So the more concerning phenomenon would be what happens under transient operation. What happens when we have larger currents flowing through the CT? Okay? So we make the statement that an unsymmetrical current or asymmetrical current which is applied to the CT, and this current is going to come. Why? Because we have a fault. Yeah? This type of current, when applied to your CT, will induce a flux, as we have written here, which is greater than the peak flux during steady state. And if you go back to what we looked at several weeks ago, it was based on the X to R ratio of the primary system. So the CT, the relay, the unit protection system, is going to be impacted by the external circuit. And there's nothing you can do about that, because that's just the nature of the beast called a power system. You have high inductance and relative to your resistance. And based on this X to R ratio, the possibility now exists. All right? Possibility now exists that we can have saturation. And that is what we are going to be looking at. What happens if my CT saturates? If this true fault, because remember, this is what we are looking at. The fault is not necessarily on the unit, but all of these external factors, the fact that I have this fault somewhere, the fact that it is on a power system which has this X to R ratio that I have to consider, it's going to create your transient. And because of that, I run the possibility of having the CTs that are supposed to provide relay information to my differential relay. The possibility now exists that they can saturate. And how will that now affect the whole operation? And that's what we're going to be looking at. So before we do that, here are the points. One, the phenomenon that we just mentioned occurs because you have differences in CT excitation. You may have unequal burdens, meaning based on what you're protecting, even the distance between the relay point or the CT, rather, not the relay point, the differences in the distance between the CTs and the relay point may be different. Simply because, well, the distances are different, therefore, the wiring resistance would also be different. If the wiring resistance is different, then it means that you're going to have a difference in burden. All right? We're talking about significant jumps in the current. So even though you may have a small burden, small difference in burden in terms of resistance, because you're now multiplying that by the square of the change in the current, that now can become very significant. Okay? The next point is that we can use what we're about to discuss, which is a stabilizing resistor. And in the figure that we drew earlier, yes, that stabilizing resistor would be your RR, which is the resistor you're now going to put in series with your relay coil. All right? So we have our stabilizing resistor, and this scheme is known as a high impedance differential scheme. So we can then end up with having, this increased current going through the relay. The question is, what value of resistance do we need to militate against this occurrence? And that's really the crux of what we're talking about today. All right, so I've been rattling on for 40 minutes. Any questions? Or this one is quite simple today. Well, as usual.
Follow it, sir.
All right. So these are the two conditions for your electromagnetic device. When saturated, the EMF will be 0. All right? So operating normally, you'd get a voltage across it. The current increases and drives the CT into saturation. Then the magnetizing winding, the voltage across the magnetizing winding, is 0. All right? And so we still have our RS. And this is just the secondary side of the CT, right? This would be your magnetizing winding. So we still have our RS, and of course, the question is this IS, this I secondary, that is going to the relay. What would we treat with it? So these are the two conditions. Operating normally, you measure an EMF. Saturated, drives it to 0. Now, remember, and keep this in the head, in the back of your mind. It isn't that the fault is on the unit that we are protecting. The fault is external, so we're dealing with true faults. If we're dealing with true faults, then the question we have to answer is, how will it then affect the operation of our system? All right. Okay, so here we are. So what I've done is just to remove the CTs, and I'm looking at just that portion where the relay coil, and the secondary resistances are. All right? And what we have over here is IF over N, because of course the fault current, the CT will just pass through the replica of the fault current. So it will be IF over the turns ratio. All right. RC would be the resistance of the relay itself. Okay. And RR, as we mentioned before, would be a stabilizing resistor. So what we're really going to be testing is if we have the principle here is that we will have current flow. We will have current flow if there's a difference in potential. That's right, go? So like networks 101. Right? Those things you have already forgot. But anyway, so we'll have current flow if there's only if there's a difference in potential. But what we are doing here, therefore, is to do a test on the system. For that, to show that Vs, yes, which will be the voltage across here. That's Vs, which is equal to IF over N, which is the current that is going to be now flowing through this. Yep. If that voltage is equal to this voltage, yes, then we'd have no current flow. Because if the two voltages are equal, then we'd have no current flow. Fair enough? You'll have a current flow once the voltage exceeds that. So what we're really calculating, we're looking for the minimum value of RR. What is that minimum under worst case scenario? That will provide the voltage balance. Don't worry. We're just going to run through an example to highlight. And when you see me use an example to explain something, you know, it's simple. I don't have to dwell too much on the principles. All right, so that's what we are looking at. We have the fault current passing through it. It has nothing to do with our equipment, but by virtue of all that we spoke about, the fact that we're in a power system, we're talking about the magnitude, it passes through, we're dealing with a differential system, right? What happens if it causes saturation? How do we treat with that? So here is an example. Do you have this?
Yes, sir.
All right. All right. So this is the principle we are using. All right. So we are looking at what happens when, for the worst case scenario, excuse me, with your external fault. Okay. So as I said, basically what we are doing is to balance the voltages. So we want to balance the voltage that to be across the relay leg or branch with Vs. And we had already shown that Vs is equal to, sorry, just going back. So this is Vs. Yep, and we're balancing it with IS RC plus RR. And remember we said that the operating current of your relay, right, is not simply greater than 0, right? It must be beyond that threshold. So there's a minimum current that is required to operate the relay. And what you're seeking to do is that when you have this worst case, when you have this external fault, which causes this massive current to pass through, you want to ensure that your differential system remains inert. It will remain inoperable. All right? So here are the data. All right? So take this question for me. We want to ensure that the voltage across the relay leg is greater than or equal to Vs. All right? Now, the question is, which of the CTs will saturate? All right? We don't know. So what we need to do is to look at each CT and determine RR. All right? Okay, so let's get cracking. Firstly, if CT1 saturates, all right, IF, which is a fault current, 50,000 over 2,000, yep, that gives us 25. And of course, the resistance values, the wiring resistance, and the secondary resistance. Yep, so we get 87.5 volts. All right, get 87.5 volts. Now, the question we are asking ourselves is therefore, what would be the value of RR that would cause 87.5 volts to be across that relay leg? And we rearrange for RR, we get 173 ohms. Everybody comfortable with that? All right, now, we then have to now look at CT2, right? So CT2, if CT2 saturates, then again, we find Vs. So now it's on the other side, right? So let me just make sure that we are on the same page. So initially, this will be CT1 saturating. Now we are saying if CT2 saturates, then IFN, because remember now, it's the same fault current, and it's a through fault current. So the same IF would be on the other side, all right? Because it's not associated with the equipment being protected. So if CT2 saturates, it's the same fault current, the same CTs we're using, right? But in this instance, the wiring resistance is a little greater. So we now have 2.5, and it causes Vs to be now 112 volts. And what we did in finding RR, we get 223. So the question is, if CT1 saturates, we require 173. If C2 saturates, we need 223 ohms. So this is where, you know, would have to apply some practicality to the whole thing, right? I'll let me back up because I don't think I had said it. You would have determined that 50K, you would have determined that to be the maximum fault current. So you'd have done a fault survey, okay? And if you recall, in your lab, you would have been exposed to fault surveys where you would be able to see what the maximum fault currents at different sections across the network would be equal to. So you now know what this maximum current is that can possibly pass through your unit. So that's how we get the 50K, all right? You know the CTs you are working with, etc., etc. So if one saturates, we need 173. If two saturates, we need 223. But of course, this is what would make it equal, yes, to Vs. But if it was greater than Vs, yes, so if you put in a resistance based on the nominal current that is required to operate the relay, if you put in a resistance which is greater than 223, then it means that, let's call that V relay, would now be greater than Vs. And Vs is what is going to be produced as a result of the through fault. Yes? So if Vs is smaller, then it means that no current, the magnitude of the current that will pass through the relay would be less than IR. Everybody with me? So what we have calculated in the 173 and the 223 are the smallest values of stabilizing resistors that we could put in series with the relay. Okay? And so the minimum value for RR would be 223 ohms. And you would go further because I doubt you'd be able to go into the shop and purchase a 223 ohm resistor. So in terms of standard values, you may end up with a 250 ohm resistor. So for this application, you would put in a minimum value 250. So the calculated will be 223 in terms of minimum because it would satisfy the condition both for the CT1 or CT2. So in effect, what we are saying is that to the extent that the protected item can handle the through fault current, we would allow that current to pass through without the piece of equipment being removed from service. And I've used the example of the transformer. I have a power transformer in my station. It is supplying 3 feeders. I get a fault on one of the feeders, which causes this massive current to now pass through the transformer. I don't want the transformer to be removed from service. What I want is for the feeder protection to trip. Okay? So you have the true fault. If the true fault causes saturation, no problem, because you are using the high impedance differential circulating current scheme, right? And by putting in that 250, the current will pass through the transformer, continue to the fault. The differential protection on the transformer will not operate. But you would limit the current on the transformer by using your overcurrent relay. Is that clear? So you're protecting the transformer from damage, but you're also maintaining the operation of your system by not tripping the unit protection on the transformer. Any questions? And if there are none, I will pat myself on the shoulder because obviously I'm getting better at getting things clear. I'm not confusing you as much anymore. All right. Okay, beautiful. So to wrap things up, I just want to open up the voltage balance scheme again, all right, and highlight a couple of things. The voltage balance scheme is used, and I'm telling you this up front, even though I made the statement later on, it's used primarily on feeders, all right? And if you note, the CTs in terms of breakout look quite similar to the circulating current method. However, the primary difference between the two would be that the capacitance. All right? Yeah, I know I'm showing electrolytic capacitance, but which it isn't, but that's the component I had at the time, right? So we have capacitance. What this means is that the capacitance, right? It's inherent to the pilot wire, even though we twist those pairs to deal with the capacitance. All right, so we don't allow the pairs to dangle parallel for the entire distance. All right, but be that as it may, we're saying that this capacitance would be as a result of the distance between the two relaying points. Because remember now that if we're dealing with a feeder, these relays would not be in the same physical position. They won't be in the same relay house. Is that clear? Because the feeder, we're looking at what's entering the feeder, what's leaving the feeder. So it'd be at different locations, which is why we are showing this, because the possibility exists. All right, but outside of that, secondary, the wiring resistance, RW2, and note RW2 is referred to one station. Right? Because one is looking at the other. So each will not accept only its wiring resistance. One is considering the wiring resistance from point H to point G. Right? Go back to H and G. Or G and H, whichever however I had it before. Right? So we're looking at the wiring from one point relative to the next. All right? Okay. So if for use of the voltage balance scheme, all right, this is the case. Now, what we said earlier is that they operate by having opposing voltages. All right? That's what we said. They operate by having opposing voltages. We'll finish with this. I mean, you have been drawing rather quickly. I'm not a cost. Then again, I keep forgetting I have the creme de la creme here too.
Sir, just one more minute, please.
All right. So, as I said, we have the EMF of the CTs, which are opposed to each other. If they are equal, if those voltages are equal, then of course you will have no current. Which makes it in effect open circuited. No current flow. That's how we describe them. So in effect, that is what we have created. However, whilst we have no current, the fact of the matter is we still have the CTs having to treat with high voltages. All right, we still have a current passing through the windings. It's just that by virtue of how they are arranged, we are not having current flow. So to avoid that, we now come to what you did in your machines. So we have CTs with large cross-sectional areas. A large cross-sectional area means that the flux density would be smaller or would be relatively small. Or we can increase the reluctance by using CTs with non-magnetic gaps. So in your machines, you would have looked at ear gaps. So you got ear gaps in the core. All you are doing is increasing the reluctance. All right. But of course, you can have floating gaps in your CT. So you would have your gaps, and maybe you would put plastic between the gaps. All right. And so we're not saying that they become a voltage source, but in terms of their operation, that's what they represents. And just by playing on that fact, which we know is true, yes, sorry, we have what are known as transactors, all right? So for your voltage balance schemes, the main consideration here is not about having stabilizing resistor. The main consideration is to use CTs that will not easily saturate. And so these CTs obviously may be a little more expensive, but to avoid the saturation, you're using large cross-sectional areas, or you're using CTs with high reluctance CTs, meaning that the gaps are in your cores, and those gaps would be filled with non-magnetic material. Yeah. And so we refer to these as, these special CTs as transactors. All right. The other points we want to make moving away from the CTs a bit, coming back now to the relays. The relays themselves, when you for voltage balance schemes, they have high impedance, not significant, right? Or not that they're not significant, but because you have the relays with high impedance, then the secondary resistance of the CTs would not be critical, because you are dealing with relays with already high impedance. All right. I remember one of the things we pointed out earlier in the module, that based on the impedance of the power circuit, yeah, based that when we referred all of that to the secondary, we saw that the relays, we could have a wide range of relays in terms of burden, yeah, because of what was happening with the excitation winding of your CTs. So in this instance, using relays with high impedance, yes, then it would not impact the CTs. And the fact that we have those connected, the secondary resistance of the CTs would be of no significance, no great significance, yes? The pilot resistance can be therefore large without affecting the operation of the scheme. And the pilot resistance that we're talking about here would be the resistance of the connecting wires. What happened here? I just lost my screen. Were you seeing this before?
Yes, sir. Just
Yes,
went
sir.
open.
I don't know what happened just now. Anyway, so the pilot resistance can therefore be large. And as I said before, the pilot resistance, could you just hold a sec for me, please? Let me just deal with something. Oh, I just realized what was happening. Hold a sec for me, please. My apologies about that. The call was coming. A call came in, so it came in on my iPad at the same time. and disrupted my screen. Anyway, just to wrap up here. So because we can deal with high impedance from your pilot wires, we also made mention of the fact that the secondary resistance of the CTs will not matter. The VBS is primarily good for your voltage balance scheme. Your voltage balance scheme, sorry, is developed for feeder protection because, of course, your feeder would be running from, leaving your substation and going over a large distance. And we pointed out earlier that that is why you have to give consideration to the capacitance. So all the other equipment that we are talking about in terms of using differential, they are all located in a small area. So your bus bars are within the substation. And the only issue you will have is that in terms of difference in wiring, it's just the position of the CTs because of where they are on the physical bus bar. Similar for your transformer. You know, we are accustomed to transformers that we possibly can see the top of. But, you know, depending on where you end up in your power experience, you may see transformers that, you know, give you a neck ache to see the top. Huge. So when you're looking at transformers like that and then look at the relative distance that the wires will have to travel to the relay house, then you're going to see those differences appearing. All right. And then let's just wrap it up with a couple of statements. So in terms of saturation, as we have just pointed out, given the type of CTs that we are using, yeah, the whole issue of saturation is not major, right? Yes, got it. Yeah, I mentioned that the stability there, but nothing major. And now, the last thing I want to say to you this evening, we're going to evening. The last thing I want to say to you where this is concerned is this whole business of spill current. It's gonna come up again. It's gonna come up again. But what we include in militating against this, or rather mitigating against this, is to use what we refer to as bias-related characteristics. We treat with the whole spill current. All right. And I'm reluctant to give you this because I think this is with 161.5, that's South Blackburn. But anyway, I'll come back to you about the bias. There's a reading here, but I just want to verify where it's where it actually is, because I think what I have given you is the updated edition of the text. All right. But for what it's worth, let me just give you the page numbers. So to treat with spill, we use relays with bias characteristics, and the whole business of bias is on page 161 to 5. But just hold on this one. I will confirm the page in the edition that you have, that I have given you. You have been able to access the textbooks, right?
Yes, sir.
Okay, just do me a favor and don't download them. I'm already at the brink of breaching our sort of copyright. All right? Just don't send me to prison by downloading the people book. Did I just confess that on tape? All right. I don't think I'll put this one on YouTube. We'll keep it in the private group. All right. All right. That's it. Tomorrow I have a whole, I don't even know how I'm going to do it, but we have a whole series of meetings tomorrow. Running into